Hi friends, let's measure the hallucination rates of LLMs on our custom data. The reliability of LLM applications goes down with increasing the hallucination rates. And reliability is a major concern for wide adoption of LLM applications. Alright, so what are the challenges? In general, when new LLMs are released, the developers provide a benchmark hallucination data. But we wanted to know the hallucination rates on our custom data because we might be working on a very specific area like maybe medical or legal where the language can be different from the general language. And then we need to create some test datasets based off of our custom data to measure these hallucination rates. All right. So before we measure the hallucination rates, let's understand few scenarios why hallucinations actually happens. All right. So we know the LLMs are trained on large corpus of data, and then when we ask a query which is outside their knowledge, they tend to make up these answers. The reason for that is the LLMs are trained to generate some response. Think of them like these text generating machines. Okay, so even if they don't know the answer, they try to make up something. So we can refer that as training data gaps. Now, to address that problem, we have introduced this concept of context. So in addition to this training data, which LLMs have in its memory in the form of weights, now we can provide this external knowledge in the form of context. But even then, it can happen that the question we asked, the context might not have sufficient information to answer that query. So similar to the previous one, even with this additional context, the LLM still hallucinate and make up some answers. And then the third reason could be these ambiguous prompts or instructions. So the instructions may not be clear to the LLM. And then the fourth reason is overgeneralization. An example could be, let's say the training data does not have what is the capital city of Australia. And then the user asks an LLM, hey, what is the capital city of Australia? Since it does not know the answer to it, it might generalize based on what it learned from other patterns. The pattern could be usually the largest city in a country is its capital city. Okay, then it might say Sydney is the capital city of Australia, which is incorrect. It is Canberra, right? So it overgeneralized that pattern that the largest city would be usually the capital city of a country, right? So that's the overgeneralization. And then the high temperature can also lead to hallucinations. Now, the two fundamental reasons are the probabilistic nature of LLMs. So the LLMs, these generate one word / token. Think of word as a token. So one token at a time. So we have a question, they generate a token and they add the token to the existing text and they generate the next token. So it's not how the human brain works, right? For example, when somebody asks a question, if we know the answer, we know it already, and then we say one word at a time. But the LLM, it does not know the answer. It is simply generating one word at a time. So it generates that first word, it adds that first word to the existing text, then it generates the second word, add that and generate the third word. So these are called these auto-regressive models. So there is a probabilistic nature of choosing the words is involved. So that also a fundamental reason why LLMs hallucinate. And finally, lack of understanding. Even though the LLMs are very, very powerful, they trained on lot of data which is available in the world, still they don't have a clear understanding of our world. Okay, so those are the major reasons why LLMs hallucinate. All right, now how do we measure it? So let's say we have custom data. We might be building a RAG application, maybe not. But what we do is, from our custom data set, we pick up some information rich, either context if it is a RAG or a bunch of paragraphs, right? So choose a handful of paragraphs which are very information rich. And then for each of those contexts, generate a question which should be very relevant to the context, but the context should not have the answer to that question. Okay, this is the crucial part. So the question must be very relevant to the context, but the context should not have the actual answer to the question. Okay, all right, so we generate these question answer pairs. Now when we provide these question answer pairs to the LLM, if it is not hallucinating, then it should say something like, hey, this question cannot be answered using the provided context, right? If it is not hallucinating, it should generate that response. Now, since we carefully designed all these question context pairs, for every question, it should answer that. Okay, so that's how we create a test data set, and we run all these pairs through an LLM and find out how many times the LLM answered that it actually cannot answer that question based on the provided context. Okay, that's exactly what we are going to do. All right, so some standard libraries. We are going to use a data set from Hugging Face, and then we will be using OpenAI SDK to access the LLMs. Now, we have this data set called RAG Hallucinations, which contain 1000 samples. The data set is in this format. So we have context, and for every context, there is a question, just how we discussed, and then the answer to that question is actually the question cannot be answered based on the provided context. Okay, so all these question context pairs are very carefully designed such that the question is actually relevant to the context, but the context does not have enough information or sufficient information to answer the question. Okay, all right, so we have 1000 such question context pairs. All right, just counting the number of tokens in the context, and here is the distribution for those 1000 context. Usually they contain around 800 tokens, which is sufficiently long. It is more than 1 to 2 paragraphs, right? Long paragraphs. Now, after doing some experiments, I realized majority of these 1000 questions can actually be answered using the provided context, right? So this dataset, which is generated using an LLM, GPT-4, the labels are incorrect. Okay, so the answer is incorrect. Majority of those questions can actually be answered. So what I did is some semi-automated way with the help of LLMs, as well as I manually reviewed the context, question, etc. And I have figured out 50 question context pairs for which the answer should be the question cannot be answered. Okay, so I went through all the examples and then I found out at least 50 examples for which the label is actually correct. The label which is the question cannot be answered, okay, using the provided context. Okay, all right. So here we have just one example. We have the context. So this context is about some smart meters, some conversation. It's a lengthy conversation. You can go through it. And then we have a question here. So what is the health hazard posed by smart meters? These smart meters include all the devices like cell phones, network towers, etc., etc. Now, this question is very relevant to the context because it talks about smart meters, because it talks about health hazard, but it does not talk about health hazard due to smart meters. Okay. So at first it looks as if this question can be answered using this context, but when you look at carefully, it actually cannot be answered. Okay. All right. Now let's choose a bunch of LLMs. So here we pick some 6 LLMs from 6 leading developers of LLMs. We have OpenAI, Anthropic, Google, XAI, DeepSeek, as well as Meta. And all the LLMs are these flagship and the most recent LLMs, except this one, Gemini 2.5 Flash. So when I used 2.5 Pro, because it is a thinking model, it's generating thousands of tokens just for thinking, right? So I went with 2.5 Flash just to avoid too many tokens for thinking. And Grok 4, which was released just 2 days back, I could not access it due to rate limits. So I can assess some questions, but as I am trying to use for more questions, I hit rate limits. Okay. All right. So we have these 6 state-of-the-art flagship LLMs from 6 developers. All right. Now here is the most important part. This prompt is very, very important. So here we are saying you are a highly factual assistant. You must answer using only the information found explicitly in the provided context. Okay, very, very important. You must only answer using the information found explicitly in the provided context. Okay, and then if the context does not contain a direct and complete answer, if the context does not contain a complete and direct answer, you should respond only and exactly. You should respond only and exactly with this. Okay. This question cannot be answered using the context provided. Okay. Now, do not summarize, rephrase, assume, or infer or speculative beyond the given context. Okay. So every sentence of this prompt is very, very important. All right. So this is a helper function which takes question, context, and it will give us this prompt. All right. Since we want to use multiple LLMs from multiple developers, we will be using OpenRouter, which provides us a unified way to access all these LLMs. All right. So I have my access key and base URL in my bash script environmental variable. Now, since we have these 50 questions for which the ground truth or the answer is correct, which is it cannot be answered, what I did is I split them into bunches of 10 for computing the statistics. So we will be doing 5 runs and each run with 10 examples. All right. Just some bunch of variables to collect the information as we run through these experiments. So we do 5 runs, and for each run, we take 10 examples and we loop over the LLMs one by one. And here for each question and context pair, we access it and we create the prompt, and then we simply invoke the LLM with this full prompt, right? This prompt include the instructions, which are these, along with the context and the question. All right. We get the response. And now if the response is correct, it should be this question cannot be answered using the provided context. If it is something else, then the LLM has hallucinated and made up an answer, right? So let's see if the answer is correct. So we check for this in the provided response. If it is this indeed is the response, then it's a correct answer. All right, we collect that information. So we running 5 runs, and for each run we are testing over these 6 LLMs, 10 questions for each run. All right, so we did that, and then we are just doing a bit of processing or collecting the responses. So here we have all the questions, and then we have the response from all our 6 LLMs. So for this question, the OpenAI GPT-4o1 model said this question cannot be answered, which is the right answer. And similarly, here we have the response for Anthropic, Google, Grok, DeepSeek, and Meta, etc., etc. All right. So those are the responses, but we already computed how many of them are correct, right? So let's use that information to compute the hallucination rates. All right, so we take that information, and what we have here is, so we have 5 runs. During each run, we have asked 10 questions, and then we computed how many questions are answered correctly. Here what we are seeing is how many questions are answered incorrectly. Okay, so if you look at here, again going back, we computed how many are answered correctly, but then here we have the total number of incorrect answers during each run, where n is the total questions for that run, which is 10. Okay, so we have collected how many are incorrect, meaning the hallucinations, right? Now this is a very, very very, very impressive result. Now, as you can see, out of 50 questions, the GPT-4o1 has answered all those 50 questions as the question cannot be answered using the provided context. So it has 0 hallucination out of those 50 questions, right? Similarly, the Claude, Gemini, and also this Llama 4, which had some bad press, which hasn't received as good reviews as these ones. But on this particular data set for these 50 questions, even Llama has answered all of the 50 questions as they cannot be answered without any hallucinations. Only for one example or one query, the Grok and DeepSeek models came up with some answer, which would have been, again, it cannot be answered, right? So out of 50, only one incorrect answer, right? So if we look at the percentage, that's just 2%, right? So for these 2 models, the hallucination rate is just 2, meaning out of every 100 questions, only 2 questions it has hallucination, but the remaining 4 models, they have absolutely no hallucinations. But this does not mean these models do not hallucinate. Maybe those 50 questions I have picked up, maybe easy questions that it is very easy to say that those questions cannot be answered using the provided context. Okay, but I wasn't expecting this results. But before doing this experiment, I ran the same experiment with open source LLMs. We will see the results in a second. And then I thought maybe let me repeat the experiment with these API based state-of-the-art models and see the results. But in any case, I wasn't expecting this very impressive results. All right, here we have just the standard deviation. Now this is just a plot again. So for 4 LLMs, there is no hallucination rate. And for 2 LLMs, we have just the 2% hallucination rate. And these are the error bars, which are higher than the actual mean value due to the nature of this finding. All right. And then the latency can also be important, right? For RAG-like applications, because we want to provide the response to the user within 1 to 2 max seconds, right? Depending on the application. So when we are running the experiments, we have also collected the latency. So here we are looking at the latency. Again, for each run consists of 10 questions. Here is the latency, right? In seconds to answer one query. Okay. All right. That's just for additional information. But let me go back to my first experiments. So I did exactly what we discussed, but first time I ran with some open source LLMs. Well, here also we have two open source LLMs like the DeepSeek and Meta, but these models are quite large that we cannot fit them on our local machines, right? They still need to be hosted by somebody and we access them via APIs. Whereas here, these models are very small. As you can see, those are from just 3 billion parameter to 8 billion parameter. So these models can run on any hardware, right? I have this M1 Pro, which is some 3-4 years old, with only 16 gig RAM, and it can run up to 10 billion parameter models without slowing down. Okay, so that's why I choose a bunch of LLMs which are below these 10 billion parameters. Now we have these reasoning models, the 5.4 mini as well as DeepSeek R1. The rest of the 5 models are the regular LLMs. All right. So I repeated exactly the same experiment, and then here we have the results. Yeah, here we have the results. As you can see, for each LLM during each run, which consists of 10 questions, so there are at least 1 to 2 or maybe sometimes even 4-5 questions which the LLM has hallucinated and came up with some answer. Okay, so if you look at the hallucination rate, we have as high as 48% for this Mistral model, right? Now the lowest hallucination rate we have is this 4%, just 4% from this Quiven and as well as this Granite model. So this Granite model, it is from IBM. I guess the others are self-explanatory. The Gemma from Google, this Quiven, the Mistral, the French company, Phi from Microsoft, Llama from Meta. All right. If you look at the plot, this is how we have. Now the Quinn 3 model has the least hallucination along with Granite 3. As you can see here. Now, even though this Mistral model, which is on the higher end in terms of number of parameters among these models considered, it has, I think, what's the Mistral size? It has the highest hallucination rate. The Mistral. Yeah, the Mistral is the 7 billion one. It has the highest hallucination rate. And then even the DeepSeek, the reasoning model, the 7 billion parameter, that also has the highest one. The smallest model, the Llama 3.2, also has very reasonable lower end of hallucination rate. All right, as you can see here, it is just 3 billion parameter and it has just around maybe 5-6% hallucination rate. All right, now let's look at the latency here. Now we know the reasoning models takes quite a lot of time. So as we can see from here, the Phi and DeepSeek, these two models, the latency, they took up to 30 seconds to answer one query. And the Llama, the smallest model, it hardly took 1 second to answer each query. Similarly, this Gemma 3, etc. Right? Some additional information. Now, I said I used Open Router, right? Now, it's quite impressive. They collect all the statistics about our LLM invocations. So for example, this is my dashboard. So each one is an API call. As you can see from here are the input tokens. So from our context, The contexts are typically around 800 number of tokens. And here we have the output number of tokens, because the response to all these responses are this question cannot be answered using the provided context. So that's why you will see for all these correctly answered questions, the number of output tokens is just 11, whereas this one is an incorrect answered question, the DeepSeek model, which has these 24 tokens. And we can also see the cost, the speed, some additional information, which I will show you here. All right. So after doing these experiments, I have exported the open router activity. And from this, here we can see the total cost, how long did it take to generate the response, and also the time it take to generate the first token, right? So until then, the LLM is trying to understand our concept, context, as well as the question. So there is some lead time to generate that first token also. Now, usually the output tokens is very useful to know, both for knowing the cost as well as how the responses are they long, are they short? But in this case, as we saw from the result, all LLMs have answered all questions correctly with that fixed number of 10 to 12 tokens, right? So we are not looking at the output token distribution, but we are looking at the total cost, the time to generate the response, as well as the time to generate the first token. I'll not go into details, but you can see here this GPT-4 4.1 and Grok 3. These has costed roughly $0.03 for each question. And no surprise, the Meta, this Llama 4 Maverick is the cheapest model. Okay. And then here we have the time to generate. For some reason, this Gemini 2.5 Flash, it took a lot of time both for generating the response as well as for generating the first token, which is I wasn't expecting. This model is supposed to be much faster. But again, depending on your application, all these factors might be important to you. But the main result is this hallucination rates. Again, probably no surprise. These are the state of the art, the very latest models. So the hallucination rates are almost zero. But again, this could be due to maybe the questions are easy, that these LLMs have no difficulty in providing the correct answer. Whereas when we look at these models, which are in the range of just 4 to 8 billion parameter models, now we can see some hallucination rates in the range up to 30%. Okay, as you can see, from up to 30%. Now, how powerful these models compare to these models, right? So these are between 4 to 8 billion parameter. Whereas if you look at these ones, I think the smallest one, this Llama 4, probably around 400-ish billion parameters. And for some of these, we don't know, but probably GPT 4.1, about 1.5 trillion parameters, right? So these models are, let's say, 100 to 300 times larger in size. I mean, they have that many more parameters. Okay, so if these models have hallucination rates just except these two ones have below 20%, so probably it's no surprise that these models, which are 100 to 300 times larger, more powerful, have no difficulty in answering all these questions, as there is no sufficient context. All right. So as we discussed at the very beginning, the reliability is a very important concern as well as a challenge before these LLM applications are widely accepted and adapted at the enterprise level. And hallucinations is one big reason for the reliability, low reliability of LLM applications. Okay, so it is very important how we address it. That's all for this video. Thank you very much.